Okay, so then welcome to the course today. We will look today into the question of how do we actually obtain our photos. So, as we said, in photogrammetry we are mostly concerned with inverting the mapping process to go from the real world to the image, which is a forward mapping process. We are looking into the inverted process. If we have those images, what can we actually infer, for example, about the scene? One of those examples was, for example, the geometry. So if we have multiple images of a scene, what can we infer about the geometry of that scene? And so today we will look into the process, how do we actually obtain photos? And what is the basic principles behind that, the kind of key elements of a camera, and then look also into what physics tells us. So there are different models on how the mapping process from the real world to a camera image actually works. And we will kind of briefly look into that today to at least give you a rough overview how this process works and what are typical errors that we encounter. So the main question is, how do we actually map the real world onto a photograph? That's kind of the key question for the lecture today. And the most important thing that we need in order to make pictures is actually we need to have light. So without light, we cannot make photos until we bring our own light sources. And this is actually something that we often do if there's not enough light, or if adding additional light simplifies the process of analyzing those images. So especially in the industrial setting, we can simplify the image processing problems that we have substantially if we control the light sources and have, for example, always a constant illumination of the scene. And therefore, lighting is a key thing. So there's no picture without light, and you know that if you make pictures in dark or quite dark environments, you may suffer from contrast issues. You may not be able to identify kind of distinct or important points very well. So it's important to have enough light, to have the right form of light, the right wavelengths of light. So the key take-home message actually is that controlling the light is important. And if we can control the light, this can substantially simplify the image or the image interpretation processes that we do. So one of the examples is if we do quality control in, for example, industrial setting. That means we have a camera over a conveyor belt where certain products are inspected. If we control the light sources and guarantee that we always have the same lighting conditions, this simplifies the process. Similar things hold for taking aerial photos and using this for example, mapping purposes. It's very hard to control the light outside, but we can actually at least consider when to fly, go up with the airplane, take those images, and if we can control or at least adapt to the weather conditions, fly under similar weather conditions or under well-suited weather conditions, that simplifies the process substantially. For example, a slightly cloudy sky is actually beneficiary for aerial photography as long as we fly below the clouds, because we don't have very strong shadows, which leads to better contrast in those images. Especially in those shadows, it's easier to analyze those images. And therefore, kind of the key important message is make use of light, of the lighting conditions, and control them, or control the image acquisition process, so if you can't control the lighting itself. So one of those examples, this is a standard scene, and we actually have different forms of lighting conditions in the same image over here. So we have, for example, areas where we have direct light here from the sun on these leaves, for example. So there's a very direct illumination of those leaves. There are also others, like this one over here, where the light comes from the back, which is a different form of lighting and can generate to different lighting conditions. And actually, for all the other leaves, the light can actually come from different directions. So here it comes actually from the side. You can see that we have some strong shadows. Some areas are very easy to identify in those images. Others are very dark and it's very hard to identify. And you can actually see from this image, depending where the light source is and where the camera is, generates different types of images. want to illustrate this process further. So if you take here a €1 coin, and the camera is sitting on top, so the camera is looking from this direction onto the euro coin. Depending on what kind of light we use and from which direction the light points to the object we want to picture, we get different types of images. For example, if the only light source is behind the object, given that the euro coin is not transparent, we actually just get a very black spot and white surrounding. The camera sits here on top. And this is something which is called backlight illumination. This is typically used if we have transparent objects or partially transparent objects. This can be useful. But even if you look from top, so if you take the directed light, so the light comes from more or less the same direction than the camera is, we actually get these kinds of images, depending if you have diffuse light or a direct light source. So this kind of, we have this diffuse illumination, but it comes all from, let's say, this direction over here. If you look into, if the image comes from the side, so lateral illumination, or also called schräge Beleuchtung, or seitliche Beleuchtung, then we actually get these types of images. You can actually see that they're less very strong overexposed areas. This is where we have a direct reflection of the light. Or we can even move more to the side towards really the 90 degrees. This is what's called dark field illumination. And we can actually see quite nicely that all the areas which are illuminated from the side actually shows a strong reflection of the light, and the rest mainly maintains black. So if I have an illumination from the side, actually from two sides in this case, it's actually an image where both sides have been illuminated, then we can actually identify, for example, small changes in the surface of those objects. So if you want to analyze the surface and see, for example, if you have scratches in the surface of an object, this kind of illumination is typically quite useful to do that, as you can see here in this image. So kind of the edges that we could extract here. Actually, it's not extracted. This is really the image that we acquire just by using the right sources, right light sources. So again, kind of all the names in German and English for those lighting techniques. And depending on what we want to do, so if you, for example, want to analyze which kind of coin that actually is, I think it makes sense if you look into kind of this image, because classifying which kind of coin it is much easier in this image compared to this image for sure, but even compared to the other images. So kind of the take-home message is, I want to illustrate here that lighting is important. We should control the light if we are actually able to do that. So it's kind of the thing which is external to the camera. If we can control it, we should control it, or we should make sure that we have similar conditions among images. This simplifies all the analysis tasks or further tasks that we plan to do with the images later on. So the next thing we actually need to look into, what are the elements of a camera, especially a digital camera? So we have some object, and some light is reflected from the object and reaches our camera. So then we have different elements which are important here. We have the lens, which we don't need if you would have enough light. So we can actually kind of avoid the lens and just put a black curtain kind of in front of our camera and just make a very, very small hole in there. As we will see later on, I can take pictures with such a system. But of course, if we have a lens, we can actually collect more lights and typically create better images. Then it's the aperture, which is an important thing, or the blende in German. This kind of the size of the opening that we have between the lens, or it's part of the lens typically, but between the lens and the chip itself. And we have also the shutter, which actually can control the exposure of depending on the camera type that we're actually using, we have a shutter or not. Or this done electronically. And then we have the sensor itself. So we have the sensor, kind of the chip on it, where every pixel is a small detector, which actually measures the intensity of light, or the number of photons that actually reach this sensor cell. This needs to be converted, because what basically the photons do, they induce a small current. Then we need to convert that into a digital signal. So it's an analog digital converter. And then we can do, a lot of cameras do some post-processing. We also have an example for post-processing we'll see also today. Kind of this is a process, and I would like to kind of look to the individual aspects of the camera system and explain kind of very briefly, what are the key elements that we need to know about lens, aperture, shutter, the sensor itself, and also the post-processing steps that are involved in here. And then later on, we will actually talk about the physics behind that process and explain briefly the three physical models from physics and how we need to have this knowledge in order to understand how the imaging process works, so how to actually obtain our images. Up to that point, is there any question? This is not the case. Actually, we'll start from here and make a tour through the individual elements here. So if we look to the lens, or in German Objektiv, that we typically mount in front of our cameras, the goals of those lenses is that we want to have undistorted images. So the higher the quality of the image, typically the smaller the distortion of the image. We should want to have a sharp image, so not as little blurry as possible, and we want to have a high contrast. So kind of the key things which are important to the lens. Of course, it depends also on other aspects of the camera. So for example, the contrast may also be, we also need the chip itself has an influence on the contrast. But from the lens point of view, these are kind of the three goals that we have when we select our lens. However, the choice for which lens we actually buy and attach to our camera, there are different parameters that we need to take into account. The first one is actually the field of view. So what is the field of view of the camera? And it's strongly related to that, how far is the camera away from the object that I'm actually considering? And what is the amount of available light? So do I need to have a camera or a lens which, depending on the maximum aperture, the maximum opening of the aperture, how much light can we actually use and how much light is available? And also the price. So lenses are typically something, the quite expensive parts of the camera. So the more you can easily spend thousands or multiple thousands of euros for a good lens. So a few examples of typical lenses, just kind of images taken from the Canon website here. So we have these tailor lenses. That means we can typically use this for picture objects which are very far away. So we have a very narrow field of view. We have something that's called a normal lens, something in the order of 50 millimeters. And then the smaller the focal length gets, the larger the opening angle. To wide angle lenses, even fisheye lenses, which can span 180 degrees or even more than 180 degrees. We can have a look to kind of what kind of images do these lenses actually generate. So if you have a moderate tailor lens, that means we have, as I said before, we have a very narrow field of view, or comparably narrow field of view. So we can actually picture objects which are comparably far away, or at least compared to the other lenses that we use. The important aspects we can also see in here in those images, the parallel lines actually typically remain parallel. So we have several parallel lines which are in reality parallel, like these ones over here, and they actually stay parallel, and straight lines stay straight, so not distorted. So this is something which is something we often want in images that we actually obtain. For example, that straight lines are still straight. At least if you want to analyze the geometry of that scene, that simplifies the process as we have. But of course, if the object is very close to our camera, and the object is potentially large, or I want to cover with my image a comparably large scene or need a large field of view, then we actually need to have a different lens. If you look to a wide angle lens, this is a typical picture from a wide angle lens over here, we can actually still see, well, the first thing we actually observe here is that we have perspective distortions in those images, but straight lines are still roughly straight. So all the straight lines in here, like those lines, they are still straight. And this holds typically for cameras with a field of view, with an opening angle of something like up to 120 degrees approximately. So we have perspective distortions. The proportions are not correct anymore in those images, but at least straight lines are still straight. If you now go a step further and look to fisheye lenses, then we actually get something like this. Even if you look to this horizon line over here, you can perfectly see that straight lines are not straight anymore. The important thing is we need to know what kind of lens we are using in order to analyze our images. So the type of lens has a strong impact on kind of what kind of images we actually get. Of course, we can apply rectifications of those images, kind of undistort those images, but this can also lead to substantial problems, especially if you want to analyze certain aspects of the image. If you look into feature extraction, something we'll do during this course, rectifying those images can also lead to problems in the feature extraction process. Because what we basically do is, depending on the location of the pixel, we kind of shift the intensity value into a different pixel in a new image. And of course, this leads to interpolation effects, which can have negative side effects. In terms of the sensor that we are considering, so what the sensor actually is, it is an array of small cells, and every cell typically corresponds to a pixel. And every of those cells actually measures the light intensity in a given time interval. So we have, if you have an exposure time of whatever, 100ths of a second, within this interval of 100ths of a second, what every sensor cell basically does, it kind of measures the intensity, the amount of light that actually reached that cell. The more light is there, the brighter it is. The smaller the amount of light, the darker it is. And what it basically does, so there's the concept of the photons is the smallest quantum of light. And what it basically does, it basically counts, every sensor cell counts those photons. And there are two different types of sensors that we typically have, CCDs and CMOS sensors. They have different properties. And one of them is quite important for reconstruction. This is the aspect of what is called the global shutter. That means the image is exposed at the same point in time compared to something, a rolling shutter. We've seen an example later on. Especially if you have moving objects, it's important to know what kind of sensor we are actually using. Also, the sensor size is important. So the larger the sensor is, and let's say the larger especially the individual pixels are, the more photons will actually reach this pixel because it simply depends on the size of this element. So the smaller it is, the smaller the number of photons that will actually reach the individual cells in a constant time interval, given that we don't change the illumination. And we can actually show that the smaller the cells get, the smaller the number of photons, and this is actually problematic for actually generating good images. And the larger that we actually make those elements, the more photons we actually collect, and the less light we actually need in order to expose the image. The only problem is the larger the chips get, the more expensive they are. That's the reason why most of your mobile phones are actually very, very tiny chips. Because we want to have them small, we want to have them cheap. But of course, this has an impact on the quality of the images that you actually take. So if you consider that to a SLR camera, which has a comparably large chip, like a 35mm chip, this of course is a much larger area for the chip, and therefore we typically get better quality images. This is just an example of typical sensors. So this is kind of the standard German Kleinbild format or full frame images. And most of the SLR cameras are here in this area. And the smaller we get, actually mobile phone cameras are even nowadays even a bit smaller than this one over here. You can actually see that's just a fraction of the area compared to, let's see, an SLR camera. And as an effect of that, a much smaller number of photons actually reach the individual pixels, which are all very tiny sensors on this device. So if we would have enough money, we would buy the largest chips that we get, unless kind of size matters for our application or for our mobile phone. And the larger the chips get, also the larger the lenses needs to be, and the more expensive the lenses are. But if we would only care about quality of the images and we would not care about price, then we would actually take the largest chip possible. Maybe not larger lenses as well, our camera gets larger, but we'd get better images. Any questions so far? Okay. Then there's certain elements of the chips that are actually important. So one of the things is the sampling pitch, and this is basically the distance between the centers of the individual elements or cells on that chip. And the smaller the sampling pitch gets, that means kind of the closer those guys go together and the smaller they get, the smaller the amount of light that we have. But the higher the resolution. So if you keep the same size of the chip, we just make all those elements smaller, we will have a higher number of pixels, but it doesn't necessarily mean that we get better quality images because all the individual cells also get smaller, and then less photons actually reach those cells. So there's also the reason why if you just increase the resolution of your camera, whatever a 5 megapixel camera compared to a 10 megapixel camera, it doesn't mean that the 10 megapixel cameras makes necessarily better images. Because we just have a higher number of those individual elements over here, but it doesn't necessarily mean that our images actually get substantially better. So the smaller the area per pixel is, the smaller the number of photons that reach that in a given time interval, and this has an influence on the noise of those individual intensity measurements. There are also elements which are important, like the fill factor, which is kind of what is the area of the chip in relation to the area of the light-sensitive areas. So kind of the overall area compared to the active sensing areas, kind of minimizing the gaps between them. But sometimes we need those gaps, for example, in order to wire electronics on the chips, and therefore it can't, or it's not zero, but we try to make it as small as possible because then we have a larger area that can be used as light-sensitive, for the light-sensitive material, which allows us to collect more photons from the same chip size. The next thing is actually how do we get actually colors? So I just said the individual cells, so these individual cells basically just measure the number of photons that actually reach those cells. So any idea on how we actually now can generate colored images? Yeah.
We divide every cell into 3 cells, one for red, green, and blue.
That will be one approach, yes. So we kind of split, we just make even smaller pixels and make some of them red, some of them blue, some of them green, and then we get our RGB channels. Any other ideas how we could actually do that?
We make a pattern, some are red and some are blue and green.
Yeah, it's actually very similar from the solution that was proposed. Of course, we can keep the size and make one green, blue, red, or we could actually make them smaller and then a green, blue, and red one. So we have a different resolution, but more or less this is kind of the same approach. Any other idea how we could actually do that?
Then you can stack 3 sensors on top of each other, and each layer is sensitive to one particular red, green, or blue light.
Yeah, so you have one problem if you actually do this approach. If you would overlay the chips on top of each other, they need to be transparent, which can be tricky if you want to do that. But the idea is not bad, so there's an approach which is similar to that.
So different wavelengths have different energy levels, so maybe you can somehow count the energy? I don't know.
Yeah, maybe that's possible, but that's at least not what is used in standard cameras. What we actually can do is we can actually use semi-transparent mirrors, or Strahlenteile in German, which reflect parts of the light. So you can actually make one over here, the other one over here, and then simply place 3 chips over here. One has a green filter, one has a red filter, and the other one has a blue filter. Then we basically need 3 different chips, and then we take a red image, a green image, and a blue image, and then we overlay those images. Or overlay, but then pixel 1, 1 of this image, pixel 1, 1 of this image, and pixel 1, 1 of this image gives pixel 1, 1 in our final image. So this is an approach which was used especially in the beginning for video cameras. The advantage is that I have for every position on the image, I have an own detector which detects red, green, and blue. So this is kind of nice. The only problem with this setup is actually, I need 3 of those chips, which make my cameras more expensive. Therefore, in most of the cameras that I use today, in all the consumer cameras at least, or photo cameras, we actually have a certain pattern. So we take our sensor grid and make a small filter on top of the individual elements. So actually the solution which was mentioned here before. So this is a filter, so only green light actually reaches this sensor cell. Only red one reaches this one, blue one this one, green this one, and so on and so forth. So we have small filters on top of the individual sensor elements so that we actually have only photons which corresponds to this window of red, green, and blue actually reach those individual cells. As a result of that, of course, the number of photons which actually reach those cells over here gets smaller because I filter out a lot of them. I only let the blue ones pass. So as a result of that, this actually gives lower quality images. First, because less photons actually reach those individual sensor cells, because I filter out quite a certain number of them. And the other thing is that I actually need to turn that into an image where I have an RGB value for every individual pixel. So if this is my image, I have a 4x4 chip, and I want to generate a 4x4 image out of that, all with RGB values. That means that I need to interpolate from the cells and then take into account my neighbors. So we have a capital character over here. It means I can take the really sense intensity for that cell, and everything which gives is kind of a small character over here means I actually need to interpolate them or compute them or approximate them from neighboring cells. So if I, for example, want to compute the RGB value for this pixel over here, so corresponding to this one. So blue, I don't need to interpolate, I can just take that directly. Red and green, however, I need to interpolate from my neighbors. So maybe I can say, okay, take the average of those pixels over here, and say, hey, this gives me my red value, and those one result in my green values. Or I may take those 3 into account for generating this one. So there are different interpolation techniques that we can actually do. And this is one of the post-processing steps that I illustrated in the beginning to actually generate color images and have an RGB value for every individual pixel. So what may seem a bit weird to you if you look to this pattern? Anything you notice if you look to this pattern? Yeah. That's actually true. So 50% of the pixels over here are actually green pixels, and only 25% are red and 25% are blue. Any idea why this is the case? Yeah.
Because the green part of the light spectrum is biggest.
Not necessarily. I mean, that's not necessarily the reason. Yeah.
The human eye is very sensitive about tiny changes or differences of green light.
Yes, exactly. So the perceived relative brightness or luminance of the human eye is more sensitive in green than in red and blue. So it's just because we as humans are more sensitive to green, the cameras have more green pixels, so to say, and so we get a better approximation of the original values because there are more green values in there. So 50% of the pixels, at least the green value we're most sensitive to, doesn't need to be interpolated. And that's the reason why we have this pattern. But this is not the only pattern. There's actually a large number of different patterns, and different companies use different patterns. So this is just an example, but the most common one is actually the Bayer pattern over here, which was exactly the pattern I was showing. But there are actually a kind of different companies or different camera systems use different kinds of patterns, and then use different ways for actually mixing those colors. But one of the things that you can actually see over here, if you take a standard monochrome camera, which has this pattern, but basically no filter at all, typically result in a better image quality compared to a camera with any other pattern, for example, the Bayer pattern. The reason for that is that all the photons, so if you look to this pixel over here, only the red photons kind of pass this filter. Here, all photons pass and get actually detected by the sensor. Therefore, if I have a monochrome image, which is generated from a chip without any filter, we typically have more photons that actually reach those sensor cells. That means we can have shorter exposure times and get typically better quality images under the same conditions. Therefore, it can make sense, if color doesn't matter for my application, to actually go for monochrome camera, because we get better quality images.
Please. Don't you change the intensity of each pixel if you filter out some wavelength?
So if I filter that out, you can basically see that it's only the green ones reaching this cell. So if you consider that the cell is basically a counter which counts the number of photons. So only the green ones will actually pass through. So let's say there are 10 green, whatever, a certain number of green, red, and blue ones. A smaller number of photons will actually reach this cell. And a higher number will actually reach this cell. And the higher there is, the smaller the noise that we typically have in the process. Okay? So the problem is now, what is the effect of using those different patterns or even different interpolation techniques to actually obtain our images? And it's something which is called demosaicing. So this is the original image that we have over here. If you take this with a kind of if I would take 3 chips for that. So if I take a bilinear interpolation, that means I take into account my neighbors and just do a bilinear interpolation of this one, I obtain these kinds of images. I know it's a little bit hard to see, but what you can, for example, should see is here at those borders, we actually make mistakes. You can see it over here. So there's some bluish area, some orangish, yellowish area over here. And of course, these errors typically occur at edges that we have in our images. If I have a homogeneous area, the interpolation works perfectly, or very well. But wherever I have a strong edge, there are images taken from, pixels taken from here and pixels taken from here for the interpolation, and this leads to these interpolation errors. And there's kind of a large number of different demosaicing techniques that are available. So this is bilinear interpolation, a commonly used one where you actually have those color mistakes. There are others, like this one actually does a pretty good job over here, but you get other kind of this checkerboard like errors that you can see over here, where this one actually did a pretty good job. And there are others taken into account prior information, which actually then generate more detailed or better quality interpolations. And there are different techniques that you can use, but something that we have to use if we have a chip which uses a pattern. So just as a further example, so what we actually have if we generate those images, if you just take only the red pixels, the blue ones and the green ones, so there are kind of more green ones than red ones and blue ones, we actually need to take those images and generate this type of image here. So if I take the original image, where I have an RGB value for every individual cell over here. Then I can take, okay, just for illustrating this purpose, I take only those pixels which are actually red pixels. And the other ones I actually make color black. And so everything which is white now is an intensity value which corresponds to those pixels which actually measure red, the red intensities. I can do this for green, so what you can see is green. The image here is kind of brighter. The reason for that is that I have now 50% of the pixels are not black, and here 75% of the pixels are black. Therefore, this one appears now to you lighter and higher intensity, because this is kind of the green channel, which has twice as many cells as the others. And red one over here. And if I now can actually combine them, I actually get my image. What we can see here is actually here, where I have all those edges over here, or here at that fence, you can actually see at least those which are sitting not too far in the back, should actually be able to see the mistakes that the interpolation process actually does. So it's also kind of the original image and the one which is generated from the process. And I try to highlight here the differences which are the most prominent mistakes resulting from the interpolation of the color values. And of course, if you want to analyze an image, especially if color matters and you're looking into small areas, this kind of interpolation can have a negative effect on the image analysis process, the process of the image analysis. So it's better to work with these images where you would actually have 3 chips, but most of the cameras today actually do a kind of interpolation in here. Any questions about this interpolation process? Although we haven't dived into the details on how the interpolation exactly works, but at least you should get an idea that interpolation matters.
Just a quick one.
Yeah.
So the left picture image was actually made with a 3-chip camera.
Okay, so in reality this was not the case. In reality this was a very high resolution image and it was artificially subsampled just to create this example, but it's kind of the same thing if you would compare this one is taken from a 3-chip camera with exactly this resolution. This would be the result you will get from a trivial interpolation, but it was just for the purpose of illustrating these results here. Any? Yes, please.
Then you subsampled for each different color.
Yeah.
They have been black and white because you only displayed the different intensities.
Yes. So everything which was black was corresponding to positions which doesn't correspond to red or green. So if you go back, so let's say the green one. So I basically show only every second pixel here, and the others are just black. It's just kind of as an illustration what the camera actually sees. So this is made for, this example was just for the purpose of generating an illustration that you can actually see this purpose. It doesn't really mean that it looked exactly like this, because the intensities that you would actually measure here would be different because some of the photons are filtered out. But as I said, it's just for the purpose of an illustration. Any further questions? Okay. We have also kind of this good old analog shutter, which can either open up at once or kind of generate a slide through the image in order to expose the image for a certain fraction of time. And so the shutter speed basically controls the amount of time that I expose traditionally the film or the chip, if I have this kind of technique in a digital, still in a digital camera, to expose the, let's say, light-sensitive material for a given amount of time with light. So the larger it stays open, the larger the exposure time, the more photons will actually reach my chip or my film, and the more light I have. So no, I like the more light, the better. Not always, but in most of the situations. But the problem is there are very long exposure times. Motion blur is an issue. So if either the camera moves or the object that I'm picturing move, I typically want to have very short exposure times, because otherwise the object moves while taking the picture, and then I get actually blurry images. This is kind of the issue of motion blur. The shutter, however, has kind of there's one important aspect about the shutter of digital cameras. There are 2 shutter things. The first thing is called a rolling shutter. What the rolling shutter basically does, it moves through an image. So in the first instant of time, let's say that just the first row of pixels are illuminated from the scene, then moves to the second one, third one, fourth one, fifth one, and so on. Of course, this happens very fast, and if the scene is static, that's not a problem at all. But if the scene is not static, that can actually lead to distortion, especially of fast-moving objects, or if the lighting changes within an image very rapidly. So just kind of as an illustration, so what I have, if this is kind of my chip, I kind of start illuminating the individual rows at different points in time, and then kind of stop doing that. And this is kind of the exposure sequence. The first row, the point in time when the first row was actually exposed to the scene is slightly earlier than the time when the last row was exposed to the light of the surrounding. Again, if everything is static, the camera doesn't move, the scene is static, that's not a problem. But if the camera is, for example, moving very fast, we actually picture different objects in the scene. So if I have one object, one bar, which simply moves fast in this direction and I take an image, I actually get this kind of image. So the bar looks not vertical anymore, it's slightly tilted to the side. That's just because at the first point in time, so when this row has been illuminated, the object was here, but when the last one was illuminated, the object had already moved. So if the movement of the object is much faster or faster than the exposure time or in a similar area, you get those effects. And if you actually Google for nice images with rolling shutter, these are kind of the two very nice examples that I found. So this is the example of a car which has been pictured driving the opposite direction. So the car moves very fast. You can actually see that this Audi car is actually completely distorted. That's just because the different rows in the image have been exposed at different points in time, and you get these effects. Or here, even the rotor blades of an airplane, which is rotating very fast. You take a picture with a rolling shutter camera, you actually see the different positions of the rotor blades at different points in time, just because the rows have been illuminated at different points in time. Therefore, it's typically better than to have something which is called a global shutter. And again, this typically depends on the sensor technology, what you actually have and can use. And that means that the whole image, all pixels are exposed from at the same point in time. So if you have the same example over here, so it's completely closed, completely open, completely closed. So every pixel is recorded at the same point in time. And as a result of that, these kind of cameras are typically used if one does 3D reconstructions, at least if you want to do accurate 3D reconstructions. And I have either objects which move in the scene, or what typically happens that the camera actually moves. So if I take pictures, let's say, from a moving car and picture the scene, and I want to do a 3D reconstruction task, it's much easier to do that with a global shutter camera rather than with a rolling shutter camera. Because with the rolling shutter camera, basically, every row of pixels have been recorded at a different point in time, and I need to estimate, for example, where my car was at every point in time where every individual row was illuminated. And this is much harder to do, and we don't need to take into account, let's say, one position where the car was when taking the image, but we need to have a position estimate for every row if you want to do a 3D reconstruction task. Therefore, these global shutters is something that usually can prefer. Even if we have a scene which is completely static, that's an example from crime scene analysis, if you have a flash and the exposure time of your camera doesn't match with the time used for flashing, you can actually have those effects that only half of the scene is illuminated by the flash, because when these pixels were illuminated, the flash was already gone or started later on. No, it should be later. So the flash fired, and the firing of the flash was over when these pixels got illuminated. And these are simply black or darker. And compared to a global shutter where you have that at the same point in time. Any questions about this process or the kind of the basic elements of the individual cameras so far? If this is not the case, we'll do a 5-minute break and let some fresh air in, and then continue with the different models from physics used in order to describe how we actually, the mapping from objects to images works. Thanks. Okay, so I would like to continue now and talk about the 3 different concepts that we have for describing light propagation. So there's kind of different ways which evolved from physics over time. Some of them allow us to very easily describe certain effects that we see, and others are more complicated but allow us to describe a larger number of different effects, and we can actually exploit different ones. We take kind of the simplest one which actually fits our purpose. The first one, that's probably something that every one of you knows, is kind of geometric optics or ray optics, oder geometrische Optik im Deutschen. There we just consider that light, for example, propagates along one ray, and there are certain things like if 2 rays cross, they have no effect on each other, and this allows us to describe a large number of effects, how the mapping from a real-world object to an image works. For some of the effects, we need to look into the wave optics. So the idea that light propagates as a wave, so there are certain effects where we can actually show that light behaves as a wave. So we have light, or the sunlight that we have is just a mixture of light coming at different wavelengths, and we can actually illustrate those waves using different experiments in physics. And the last one, something which is called quantum optics or particle optics, or Quantenoptik, which is based on the idea that there's a so-called duality between, or wave-particle duality of the light. So in some situations, the light actually behaves like a wave, and in some situations, it behaves like a particle, although some other effects can only be described as a wave or as a particle. And this is something which is a part of quantum mechanics, or a subfield of quantum mechanics. We will start actually with the geometric optic or ray optics, and most of the things that we actually do can be described using this theory. And it has 4 basic axioms. The first axiom is actually that a light ray actually is a straight line in homogeneous material. So if you have this, if it travels to the same material and it's a homogeneous material, so that means it doesn't change its density, for example, the light actually travels along a straight line. Next thing that we can do, if we have 2 materials and the light travels through those 2 materials, and at the border the light is either reflected, or parts of it is reflected, and parts of this is actually refracted. So refraction is Brechung in German. And depending on the type of material, we have different refractions. And the next thing is that the optical path is actually reversible. So it can travel in one direction as well as in the other direction. And if we have 2 light rays, let's say one pointing like this, one pointing like this, and they intersect, they actually don't influence each other. So these are kind of the basic 4 axioms of the geometric optics. So light travels along those rays, and we have a speed of light, which is approximately 3 times 10 to the power of 8 meters per second in vacuum. And if other materials, the light travels at different speeds. And this depends on the refraction index that we have. This is something which depends on the material. It's 1 in vacuum. Then actually the speed can be expressed as the speed in vacuum divided by the refraction index. And the key idea behind that, the light always travels the fastest path, along the fastest path. So depending how it goes through the different materials, how the refraction is done, full of these ideas that the light actually takes the fastest path. Now the most important thing that we actually use in here is that the light propagates as rays from the different light sources. So let's say we have a light source, somewhere the sun over here, and it illuminates this object, and we have a reflection from the object. So we take this as kind of a point source where the light is actually emitted, or where it is reflected in our situation. Okay, so the first idea, if you want to build a camera, we can take some film or light-sensitive material and actually place it here. So with the idea, if we have a light source which illuminates this object reflects the light, and then we collect this light here on this material. If we do it like this, we actually have the problem that, let's say, all the light which is reflected here hits the film at all the different positions. The same holds for the light which is reflected here and here and here, and actually at every point. We actually get this reflection, and the rays hit all the locations on our film or on our chip. So what we actually measure here doesn't allow us to get any information about this object. This is something which doesn't help us to generate good images. What we want to have is that all the reflected light from this point just reaches one single point on the film, and we want to have that for all kind of distinct points here in the 3D world. So every point, at least along this surface over here, should be mapped to only one specific point on that film. What we can actually do in order to achieve that, we can actually introduce a barrier with one small hole in there. So all the light which goes from here onto this barrier simply doesn't reach the film. So it's, for example, reflected away or absorbed on the material. But this ray over here, which passes through this small hole, will actually be mapped to this point over here. And for the blue one will actually be mapped over here. And the trunk of the tree will actually be mapped somewhere over here. So if we introduce this barrier, we actually obtain an image where every distinct point on this surface is actually mapped to a distinct point on the image. That's exactly what I want. Of course, it doesn't hold for all objects in the 3D scene because of due to the occlusions, but let's say if I have a flat surface, I would have a flat surface over here. Every point on this flat surface would be mapped to an individual location on the film. Okay? So the effect is that given that the individual point on the surface is mapped to an individual point in the film, this actually reduces the blur that I had here. So I had kind of infinite blur over here. If I, of course, make the hole slightly wider, then a few more beams will actually pass here. And this point is not one distinct point, but let's say a small area over here. Same holds for here. And the larger I actually make this hole, the larger the area of blur gets. But the more light actually reaches the film. And this is kind of the trade-off that I always have to make. What's kind of the amount of blur I'm willing to consider given the fact that more light actually reaches my film or my sensitive material. And depending on what's the quality of the human eye, we may say, okay, a certain hole size generates sharp images. From a certain size, actually the images get blurry. And this is what is called the pinhole camera, or Lochkamera in German. So we have our object over here, like the candle. We have this box over here, which is my camera, the small pinhole over here, and this maps this object onto the image plane, actually being upside down. Often, this is kind of illustrated as putting a virtual image in here. It's kind of the same image, kind of rotated around this point, so it sits over here, that is actually standing upright. But this is just kind of, one often uses this kind of illustration in order to make the process easier to understand. What happens inside the cameras, but actually is actually this one. But of course, I can take out the image and just rotate it. The process of generating images like this is a very, very old process. Actually, it dates back around 500 years ago. And it was actually used in order to observe an eclipse of the sun, because you don't want to look into the sun, but you can actually go into a dark room with a small hole, and then you actually see the image of the sun that you can actually see over here without actually destroying your eyes. This one, where this was at least first documented to be used in 1544 as what is called camera obscura, or dark room. So you have the eclipse of the sun, it's projected through a hole into a dark room, and they can actually observe this phenomena. So it's a concept which is very old, even much older than the knowledge of light, light-sensitive material. One can, of course, also use this to actually put a piece of paper here and let someone paint a scene. It's also something which has been used a bit later in order to draw a photorealistic painting, so to say, of a scene by using the same technique as a photo, but someone simply drawing what he sees here on this black wall. And you can actually generate such a camera at home if you close your blinds at home and have a small hole in your blinds. After your eyes get adapted actually to the darkness, you can actually see that the scene outside the window is actually sitting upside down on the wall. And you can actually picture that. And then, so what you see over here, of course, if you want to make a picture like this, you need to have a long illumination time of your camera if you want to take this picture of this wall. But you can actually do that. This is the example where this has been done. So you make a small hole in your blind, close the blind completely, and then illuminate, take a picture of that scene, then you will actually see what's going on outside. Something you can easily do at home. Any question about the idea of this pinhole camera? Okay. So let's go a step further and look, okay, what's behind this pinhole camera model? How does that work? So this is our real world. So this is a point in the real world, x, and this distance here is x. So everything which is in capitalized letters is in the world, and everything which is a small letter here happens in the image. This is our barrier, our hole or pinhole, and we see, okay, that this point actually gets mapped to this point down here. The first thing that we can see is, depending how far we are away from the barrier over here, so this distance z, depending where it is, the image actually gets larger or smaller. Also, the further this one goes away, the smaller my image gets. And the closer it comes here, the larger my image gets. This is something to the image scale. This is kind of related to this distance, the ratio of those two distances. So if it's a one-to-one relationship, so if capital Z equals small z, then actually would generate an image which is of the same size as the real object. So in most real-world situations, we actually have the fact that the image that we generate is much smaller than the object in reality. But you can also imagine the other way around. If you think about macroscopic photography, we actually take a picture of an object so that the pictured object is larger than the object, the original object. So we can take actually any values in here. So it does not necessarily means that the pictured object is always smaller than the object in reality. And we can also compute a mapping. So if we know those distances z, we can actually say the size of this object over here is actually given by this factor m times x. So we only need to know m in order to estimate where this point in the real world is actually projected to in the image. The problem that we have, if we want to use this in reality, is that if you use a pinhole camera, for most applications, the hole needs to be so small to generate a sharp image that not enough light actually reaches the film so it can actually be used very well. So we need to have more light in here for realistic applications. That's the reason why we have lenses. So we can now add a lens. So we move from this kind of model towards using a lens. So now we have a lens over here. We have the effect that, for example, the light coming from this point x over here, so everything which goes here on a straight line changes the ray changes its direction due to the lens and reaches this point x over here. Which also corresponds to this straight line. Now the problem that we have is that we also need to add a barrier, the aperture, which actually closes this down. Otherwise, we again have this completely open sea. And the smaller we actually do make the barrier over here, the closer we come to the pinhole model, the sharper our image typically gets, but the less light we have. So depending on how you control the aperture size here, basically means you control how much light you actually generate in here. And this point over here is a so-called focal point. So all those rays, the rays over here from this line go through this focal point and generate our point x in here. And so we actually move from here to here, and one of the central equations is a law of thin lenses, or Linsengleichung in German, something that you've probably seen in physics in school, that you actually can relate the focal lengths over here, the distance from the lens to the focal point, depending on the individual z values of how far the object is actually away. So it means you have a different focal point depending on where your object actually is. And then you can actually equivalently formulate the Newtonian lens equation, which relates the focal lengths and the points z. So depending on how far your film is away from your lens and the object is away gives you your focal point. And if you kind of change the focus of your camera, what you're basically doing, you're changing that. And this way generate a sharp image. Of course, this thin lens is just an approximation of the pinhole. So you can see the using thin lenses is an approximation of the pinhole, but it's definitely not a perfect pinhole. It's kind of the fix for the problem that we don't have enough light in order to use a real pinhole model. And as a result of that, as the hole is typically never small enough, we don't have enough light to illuminate the scene and detect all the different intensities that we would need to detect with our chips. We need to introduce a lens, but the lens is always an approximation. And the quality of the lens actually has an impact on the quality of the images that we actually generate. What we can do is we can actually use the aperture to control the kind of which part of the lens is actually illuminated through the scene. But just introducing a barrier. The smaller we make the barrier, the sharper the images gets, because the smaller our hole gets. And the more we open it up, the more light we have, but the more blurry our image actually gets. And this is something which quite quickly leads to something which is called the depth of field. So this is an image taken from a scene, and you actually have only a small area over here where the image is actually sharp. It's probably from somewhere over here to somewhere over here in this area. Everything which is closer, it's not a sharp image. You see the glass here or the object in the back. You can even take a picture of those of these words over here, which are not on a plane surface, and depending on your aperture, you actually get a different depth of field. So this, typically, the smaller you make the hole of the aperture, the larger is your depth of field, because the closer you actually reach the pinhole model, and the more you open it up, the more blurry, or the larger the area in which is blurry, it's not sharp is. And you can actually, so in photography, if you want to generate beautiful pictures, you can actually use this, for example, putting focus on, for example, the face of a person. You would make, if you open up the aperture so that the hole gets larger, you have a very small depth of field. So, for example, a face is sharp and everything is blurry, which you can actually use in order to generate nicely looking images. But that's not necessarily something we're looking into in photogrammetry. We would like to have that sharp in order to do our measurements. And this is just an example, and depending on the different values, so this is a comparably small hole of the aperture, and here you open it up larger, you can see a very small depth of field over here, so those faces are barely visible, recognizable. Here you may be able to recognize, and here they are comparably sharp. This is one of those examples. And the next thing I would like to do is explain why this is the case, where this actually comes from. We can actually nicely illustrate this by this figure. This looks a little bit scary in the beginning, but it's actually not. So we have here our lens, and this is the aperture. So the smaller this gets, the closer we reach the pinhole model. What we have in here is kind of the location of the sensor, or our traditional film, which sits somewhere over here. Okay, and we have different points in the scene, in this case, along this ray, so this point xn, x, and xf. And the point, as we see now, this point xn and xf can now be used to describe the depth of field. So if you consider this point over here, so every ray of light which is reflected in this direction doesn't reach my film due to the aperture. So the last beam that actually reaches the image plane is the one over here, which is then moves down here. So this gives us this point over here. Actually, sorry, this point down here. We can do the same for going down here. So that means we have this area over here, which corresponds to this area over here, where from xn to xf is actually mapped to. So depending where we are along this ray, will be mapped to the same location, but kind of blurry along this circle of confusion or Zerstreuungskreis. This one over here. And so the larger this gets, the more blurry our image looks. If we close this blind, those points move closer together, and there will be kind of the area gets smaller and smaller and smaller over here. So it's kind of the closest point, which goes here, and the point which is furthest away, describe the size of this Zerstreuungskreis over here. And if it is small enough for the human eye to be seen as one single point, we have the impression of having a sharp image. And the larger it gets, the more blurry this gets. What you can also now see, if we move, so this kind of gives me then the depth of field, if this is smaller than a certain size. If we now move the objects further away from the scene, so we actually move in this direction, that means this angle over here gets smaller and smaller and smaller and smaller. That means this guy also gets smaller and smaller and smaller. So the further we are away, the less we can actually control the depth of field. The closer we actually move to the object, the larger is the angle. You get this angle over here. And as a result of that, the smaller the depth of field. So if you have an object which is very close to our camera, with a fixed aperture, the depth of field is really small. The further we move away, the larger it gets. Okay? The reason for this is because if I move those 2 points further away, this angle gets smaller, so I can kind of move one point faster than the other. That means this size gets bigger if I want to keep this size constant. So kind of to sum that up, we have different points along this line, and depending where that is, the point will be mapped to different points in here. And the further we are away, the one point moves away from the other, the larger it gets this, or smaller it gets this. The point, or the area to which the points are actually mapped to in our image. And kind of the smaller this gets, the sharper is our image. And simply at some point in time, if this one is larger, then kind of the resolution of our eye, we say, okay, now it gets blurry. It's kind of the key explanation for the depth of field for the cameras. Okay, so the key assumptions that are actually made in the pinhole camera model, or actually in the if you're using a lens, so the assumptions of the pinhole camera, which we also use if we use lenses, is that all rays from an object point intersect in a single point, our focal point. The other thing is that all the images actually lie on a plane, so that actually this is a perfect image plane over here. And the third one is that the ray from the object point to the image point is a straight line. So that this thing is actually a straight line. But you're going to see already, in terms of a lens, this is not the case. So what we're doing here, we're using assumptions, and we still assume in a lot of applications that we still have a pinhole camera model, although we in reality don't have a pinhole camera model. The smaller we actually make the aperture, the smaller the hole actually gets, the closer or the smaller the approximation errors that we actually do. This is kind of one source of error that we have. The other sources of error are actually mistakes or errors in our lenses. So these are deviations from the perfect mapping that we have, due, for example, to the quality of the lenses that we use. And there are different types of distortions, and I just want to give you an idea of what kind of different types of distortions are and kind of illustrate the effect of these distortions. So one of the things you typically see, especially if you use a wide-angle lens, is actually a barrel distortion. So if you have a grid and you make a picture of those grids, you can actually see this kind of barrel distortion. And it basically depends how far you are away from the center of the optical axis, or the principal point over here. So the further you go away, the more you have this barrel distortion. This is the reason if you take a portrait of a person with a wide-angle lens and the person is in the middle, the face looks blown up. This is exactly this barrel distortion. or you can have the inverted, but of course you can correct for that. So you can actually, if you know about the properties of your lens, you can do a rectification of the image. And what you basically do in this situation, you take the pixel over here and shift it a little bit more to the inside. And the further you're away from the center of the image, it should be this one over here, the larger you actually correct this point. So basically you have, you translate every pixel to a slightly different location, and this leads to a rectification of the image. You can have also a pincushion distortion, which is exactly the other way around, and even combinations of those. These are kind of standard distortions, especially those appearing if you have wide-angle lenses. The other thing we often find is a spherical aberration. So in the ideal case, if we have parallel lines which reach our lens, they should actually all intersect in one single point. Was the idea of the lens. If our lens, however, is imperfect, this is not the case. So depending where we actually, where the ray hits the lens, this is actually intersects at a different point. As a result of that, again, if I close the aperture, which basically I'm filtering away beams, this effect gets smaller and larger, smaller. So the closer, so the barrier goes up to here, I'm more or less in this ideal situation because all the larger, further I'm away from the optical axis, the larger this effect here gets. But this is, again, these are all small errors we see in typical lenses that especially standard consumer lenses that you buy. You have different types of these corrections. And one thing you can typically see is the chromatic aberration if you have a standard, even a standard SLR lens. And that is that if you look, the change of direction of the light which comes in here depends slightly on the wavelengths. And so these are three parallel, the red, green, and red light coming from one single point over here that will actually be mapped into different locations. And one tries to do what in standard lenses, one actually use different lenses with different materials and try to kind of compensate for this effect, to get rid of this chromatic aberration. But you can see that, especially in wide-angle lenses, because the further you away, the larger this effect gets. If you have wide-angle lenses, you can sometimes see these kind of different stripes of colors at borders. And this can be a mosaicing effect, or demosaicing, so the interpolation I presented before, but it can also be effect of your lens that you have that because the direction where this ray actually ends up is a function of the wavelengths, at least to some small degree. The next thing is something that people who have glasses may know, astigmatism. This is basically an effect that you don't have a perfectly circular lens over here, or that your eye is not a perfect circular lens, and that you have a different focal point in the horizontal and in the vertical direction. So you can see that in this direction over here, the focal point is here, and in the horizontal direction, it sits over here. And depending on which correction you do, in terms of changing the focal length at the global thing, you won't see a sharp image, unless you explicitly compensate for the effect that you generate a lens with a different focal length, to compensate the error of the eye. But even lenses can actually have that effect. This was called astigmatism. And the last, or more or less last, is what's often called a coma or chromatic aberration. This is actually a combination of the spherical aberration, which was this effect over here, and an astigmatism and then if the light doesn't come in parallel to the optical axis, you actually get this effect that also those points don't meet in the image plane, then you can get this kind of tail-like structure. So you would expect the object to be here, and you actually get this kind of tail, like a small tail of objects. So you don't see that often anymore in lenses, but still, small effect can be visible. And last but not least, some effect that you see, or that is typically used in whatever Instagram pictures quite frequently, and that is artificially added because nowadays the lenses are so good that this effect is typically small, is that you have the areas far away from the optical center actually are darker than those in the middle. And this, you can still see that if you have a lens and you open up the aperture completely, you sometimes still see this effect, but if you buy high quality lenses, this effect is typically very small, and now we actually add computer programs to kind of regenerate this effect of the old days. You may ask yourself if this makes sense to buy a very good lens and then manipulate the pictures to generate the effects of really shitty lenses, but that's what is often seen as beautiful. At least you can use this, for example, to focus the center of attention to a certain object. So this may make sense, but generating those kind of pictures from a real camera is quite a while ago, and luckily it's quite a while ago to generate those. And these are all effects we can actually describe with the geometric optics. So assuming that we have kind of this rays of light moved through the scene, we can describe these effects using this mathematical or physical model in order to do that, based on those 4 axioms that I presented in the beginning. The next thing we can do is actually look into wave optics, considering that light propagates as a wave. So what it basically says, it goes back to Maxwell's equation describing electromagnetism and saying that light is electromagnetic radiation of a certain wavelength, at least the visible spectrum that we have, of a certain wavelength, and it behaves like an electromagnetic wave. So you have things like inference, for example, which is the effect that if you have 2 waves, they can overimpose each other and cancel out each other. So I think you all have seen that. Have you all seen that in physics? What do I have to explain? Okay, so I don't need to talk about that. So the idea is to describe light as a wave. We have wavelengths of the visible spectrum somewhere from 400 to approximately 700, and it's just a form of electromagnetic radiation. And certain effects can only be described with this kind of formalism. And if we look to the whole spectrum of electromagnetic radiation, we can actually see that the visible spectrum is just a very, very small spectrum that we can see over here. And for example, infrared, so it's kind of everything which comes here, is also something that we quite often see, for example, if we monitor vegetation, for example. Vegetation reflects infrared light quite substantially due to the chlorophyll we have in plants, which leads to very high responses in the infrared spectrum. Therefore, for example, these parts of wavelengths can be quite beneficiary if your goal is of monitoring plants. And so different electromagnetic radiation has different advantages if I want to observe certain phenomena. But we mostly stay here in this visible spectrum. Also, one of the things which we need later on, which is important, is kind of if it is a wave, this wave has a frequency, and the frequency is related with the wavelengths, and it's actually the speed of light divided by the wavelengths as a frequency. So these kind of inverse, the smaller the wavelengths, the larger my frequency gets. So the length of a wave and the frequency that it is. And this is in vacuum, and if I have different materials, of course I have the refraction index of that material that I have in here in order to describe the frequencies. And these frequencies, you can also see, depending on the energy that the photons have in the particle optics, this corresponds, can you see this corresponding of a photon corresponding to a different wavelengths, that is also related to the energy of the photon. Again, not only the visible spectrum is important, also the, for example, near-infrared spectrum or things near the visible spectrum. Here are 2 examples. So this is actually the same scene recorded once with a standard RGB camera and once with a near-infrared camera. What you can see here, actually the tree, which is quite dark in the RGB spectrum, kind of, it's highly, highly reflective in the near-infrared spectrum. And the reason for that is that there's a strong reflection from the chlorophyll in the plants, or at least in the living plants, that generates this reflection. Therefore, if you want to monitor vegetation, taking into account the infrared spectrum is very, very helpful, for example, for separating vegetation from other objects in the scene, or for for analyzing those plans. This is also an image here, an aerial image of where there's a change. The near-infrared, so the near-infrared spectrum replaces the red spectrum. So there's kind of a change in the spectrum, but you can also see that the vegetation of the grass kind of sticks out with a very high intensity. So it's very strongly red areas. We can perfectly or very, very easily separate the vegetation from the non-vegetation over here. Also, other parts of the spectrum are relevant if you look into microwaves. So wavelengths of something around 1 centimeter. We can actually use this to look through clouds, which is something which is very relevant if you look into monitoring the Earth from satellites, because you can be weather independent. And it can also be used, for example, to estimate the water content in the ground or in soil. And therefore, whenever you do water monitoring, this is a frequency that you typically consider. And last but not least, I would like to quickly or shortly dive into the idea of particle or quantum optics. So the main idea here is that the light can actually be treated as a wave, and it can also be treated as a particle. So it's kind of what's called the duality or the wave-particle duality. And so it takes into account the fact that some of the effects that we see can only be described assuming that light is a particle, and other effects can only be described, well, if we say it is actually a wave, light is a wave. And the theory kind of combines the thing that light can actually act as a particle and act as a wave. And it's especially important, for example, for describing the effect that I want to measure the intensities with a sensor, because what actually happens in this description that we have this particles, energetic particles, the photons, which actually hit the sensor cell and induce a current in this cell. And I can actually measure those currents, and this gives me information about the intensity. And the more photons actually hit this cell, the higher the intensity. And this is one very elegant way for describing this interaction of the photons with the chip itself. So the key idea in there is that the photon is kind of the elementary particle of light. It's kind of the quantum of light. There can't be half a photon of light. The photon is kind of the elementary unit. And the energy of my photon actually, Q, depends on the frequency and depends on a constant. So H is just a constant, a very, very small constant. And so if I multiply this constant by the wavelengths, it gives me the energy of one photon. And then if I kind of increase the number of photons, I have multiples of these energies. So we can have an example. Let's say we have a photon which corresponds to a wavelength of 700 nanometers, so something like a red photon, if you want to describe it that way. We say, okay, we have the Planck's constant and the frequency. The frequency is the speed of light divided by the wavelengths. And then I end up with this equation over here. Just get rid of the values. And it turns out that the energy of the red photon is something like 2.8 to the power 10 to the power of minus 19. Watt seconds the same than joule. So it's a very, very small number of energy. But therefore, I need a multiple of those photons typically in order to detect it on my chip. So if this is my chip with different cells, and let's say I have sunlight over here, and the sunlight emits photons. What basically happens, the photons induce a current in these individual cells. I can measure the current that is induced in these different cells. And the more current I measure, the higher the intensity. And typically, this is actually a linear relationship based on the number of photons I have. So whatever, 1,000 photons is half as bright in the terms of the intensity that I measure with my chip than 2,000. This is all I want to say about photons, but at least we need to be aware of that we need different physical models in order to describe different effects that we see with light. So some of the effects can only be described as a wave, some of the effects can only be described as a particle. Most of the things that we actually discuss here in this course actually we are fine with the geometric optics or ray optics. The last few words about lighting and reflectivity. We said in the beginning of the lecture here that lighting is very essential, and the question is now, how does reflection work? Because in the end we have a light source, the light hits an object, and it's reflected in different direction. So if we have here a surface, we have a light source like the sun, it illuminates our surface, and then we measure that surface with our camera. So for example, this pixel over here corresponding to this pixel. And the question is, what is the amount of light that I actually can observe here? So this clearly depends on the light source. The more energy or the more light is emitted from this source, the more light we can actually receive here. But it also depends on the surface. So it will depend on the material, and it will depend on the shape of the surface. And there's a general model which is called the bidirectional reflectance distribution function, or BRDF, which is a function or distribution which describes me in what's the reflectance of a material depending on its surface and on the wavelengths of the light. And this is something which is extremely essential in any, for example, computer graphics application if you want to render a scene. So for every material I need to describe, or at least if I want to get a good results, this BRDF function, or the BRDF function of the corresponding materials that it should be, which describes me how the light is actually reflected. Because this generates me the intensity of light that I actually will see from my camera or my virtual camera. Mostly this depends on the surface and the surface normal. So what is the deviation of the surface normal? And most of the materials are actually isotropic materials. That means only the distance from the normal actually matters. So I can actually simplify this equation that it matters how far am I here away from the normal, and the difference of these two angles, but not actually their actual values. So depending on from which side I actually look to the material, I get the same type of reflection. We won't dive into the details of this BRDFs. The thing is actually estimating BRDF functions for materials, something which is quite tricky. So if you go to some of the computer graphic labs here, they actually have a big dome with a lot of cameras, whatever, 60 or 80 cameras, observing an object from different locations. Then you can actually illuminate this object, take all the pictures and measure and generate a model for this BRDF functions, which you can then use in order to render materials photorealistically. So if you want to do photorealistic rendering, means understanding how this process works of generating an image from an artificial light source, because what you do is you generate an artificial image. This actually becomes very relevant. Or if you want to do a 3D reconstruction of a scene, say a scene you have pictured with cameras, you want to generate a 3D model and want to generate a photorealistic impression that you as kind of virtual person can virtually walk through the 3D model, you actually need to take into account this BRDFs in order to generate a photorealistic experience. Also, kind of the amount of light which is reflected depends basically on the incoming light and this BRDF function. And of course, depending, you don't want to look from it from below the surface, at least if it's not transparent, the material. And basically need to integrate over this BRDF and the intensity of the input. So it's really, the BRDF is a density of which you need to integrate in order to obtain the amount of light that is in the end reflected. That's basically it. Last but not least, there is, if you kind of simplify this reflection even more and just see it from an abstract point of view, we can say that different materials reflect the incoming light at different intensities. And one of the things to describe this is actually the albedo, which is a value between 0 and 1, which basically means if the value is 0, it basically nothing is reflected. If it's 1, all the light is reflected. And if it's 50%, kind of only 50% of the incoming light is actually reflected. And what you can see is here is that most of the things we are actually interested if we monitor the Earth is somewhere in this area here. Let's say somewhere between 1 to 5% up to maybe 50%. Unless we, let's say, monitor glaciers, we go up higher in these areas because they are highly reflective. But everything happens actually in this area over here. So if we look to this relevant area, we can actually see that we have relevant values of these albedos of easily 1 to 50, 1 to 100. Especially so if we have kind of trees or Nadelwald, for example, has very low values, going down even down to 2%. And the important thing to know is if we take into account the incoming light, and we want to see certain contrasts, so differences of materials down here as well as materials down here, I actually easily require a large number of different intensity values that I can actually map. So if I can distinguish 1,000 different intensity values, I may be able to see kind of differences within the forest or within, same point in time, within ice. So the question is now, how many intensity values does actually a regular camera provide? If you have your regular digital camera, you take a picture, how many intensity values do you actually get? Yep, from 0 to 225, so 256, sorry, 256 values. So that means what you actually get, if you look to your standard JPEG or PNG format, it's actually for every of those channels you get only 256 different possible values, which is often not sufficient for doing those monitoring tasks. The good news, however, is that most of the chips actually can distinguish more intensity values. And therefore you have actually the raw format, which some of the cameras, or most of the cameras provide nowadays, which actually offer 2 bytes per channel. So in theory, you can at least have 65,000 different intensity values per channel, which is typically sufficient for most of the application. So the question is still, does the chip support that many? Often this is not the case here, typically sometimes around 10-bit or 11-bit, but this is a number which is actually increasing as chip production gets better and better. With this, I'm actually coming to the end for the course today. So what we have looked into today, or what kind of your take-home messages, what you should have understood is kind of what is the basic principles of cameras? What are the key elements of a camera? In which way do they contribute to the image acquisition process? And what are things we need to take into account if we want to minimize a certain error? For example, blur. Aperture is one of the things you can actually control. Then you should have get at least rough idea about the physics behind the process or the phenomena of light propagation. So there are different ways to describe that, different models of different complexity, and those models can be quite easy, like ray optics, but they cannot describe all the phenomena. Depending which phenomena I want to describe, I need to go to more complex models, in the end ending up with particle optics. You should have understood what the pinhole camera model is. That's actually pretty important, and most of the computations that we do later on in this course are actually based on this pinhole camera model. You should have understood what are typically errors that I may get, for example, from my lenses, things like astigmatism or barrel distortion. Some of the things we can compensate, some of the things we cannot easily compensate. And we also looked into very briefly in the end, on reflectivity. So the material matters, the illumination matters, and basically the normal of the surface matters. They're kind of the 3 things which matter in terms of what is the amount of light that I can actually perceive with my camera. That's it from my side. If you want to look into that, again, the script of Wolfgang Förstner, chapters 2 and 3 cover what I explained here. Some of the material actually comes from the Zelinsky book, which also gives you a very nice, even more detailed description on the camera processes, the different effects, the mosaicing effects are very well described in there. Are there any questions from your side now? If this is not the case, thank you very much for your attention. See you all on Thursday, actually, and tomorrow there is the exercise at 12:15. Thank you very much.